All right, what's going on, everybody? So today we want to start to look at determining independence between two categorical variables. So this is something we kind of conceptually looked at in the first unit. And actually in the last chapter of AP Stats, we're going to look at what's called the chi-square test for independence. That would allow us to look at the same thing. Are two things independent? But today we want to view that through a probability lens. So let's do it. So are blank and blank independent? That's the question. And so as we start here, thinking about the vocab, like that sweet picture over there, you see what I did there? As we think about independent, how come my pen's not working? As we think about independent, right, that means not related. So just in terms of vocabulary, independent means two variables are not related, not independent, right? That means they're related. So sometimes, right off the bat, the vocab can be tricky. So here we go. So as we try to determine independence, again, without using our chi-square test for independence, that'll come later, but using probability formulas, we've got two options. So there's two ways to try to explore whether two categorical variables are independent or not. One option is based on this and means multiply rule. So and means multiply if our events are independent. That's kind of the rule we learned. We can write that out this way. The probability of A and B is equal to the probability of A times the probability of B if events A and B are independent. And so we can just use this rule, apply this in reverse, maybe the converse. If A and B are independent, then A times B should give us A and B. And we'll see that used in a second in an example. But so we can apply this idea of checking to see, does A times B give us A and B? Right, that's what that means. And if it does, that means our two events are independent. So one way is to apply this and means multiply idea. And we'll see that in a second with the 2019 free response. The other option we have is to use what's called the independence formula. And so the independence formula says if, whoops, I didn't mean to put that comma there. If A and B are independent, so if some events A and B are independent, sorry, I know that's sloppy, but you know what it says. If events A and B are independent, then the probability of A should equal the probability of A given B. Essentially, what we're saying is this like given B didn't even matter, right? Given B didn't change the probability. We ended up with the same answer as the probability of A. So in other words, the given B happened didn't affect the chance that A occurred. So B kind of had nothing to do with A. Those events are independent. Or I could say the probability of B should equal the probability of B given A. So this is the independence formula. This is the type of logic we used when we were looking just at two-way tables and thinking about categorical data in our first unit. We were thinking something like this. We were trying to compare like what's the probability someone takes AP Stat versus does that equal the probability someone takes Stat given we know, say, they're female. So if, let's say, given we know someone's female, maybe the probability they take AP Stat is 0.7, maybe the overall probability someone takes AP Stat is 0.5. This showed us that if we knew the person was female, it increased the chance that a person took AP Stat compared to overall. So it seems like being male or female, being female is related to taking AP Stats, right? Because given we knew you were female, we get a higher probability of taking AP Stats than overall. So these were the types of conversations we had previously. Now we're just assigning a formula to that same type of idea. So two options, and means multiply or independence formula. So let's see how we could use both of those for the 2019 free response. So we looked at this question the other day in our class, and we skipped over part B at the time, or maybe just thought about it as a bonus. But so here we want to look at, for the people surveyed are the events of being a person whose response is never and being a woman independent. And we got to justify our answer. That means we got to show some math. So there are two different ways you could do this, and we'll look at how to write it up. One way is using the and means multiply approach. And so previously in this question, we found in A1, right? So this was question A1 you would have done previously, the probability that someone's response is never, and they're a woman, that was 0.0636. Jumping back up to the table, the probability someone's response is never and they're a woman, that's this spot right here. So probability of never and woman is just that 0.0636. I forgot what happened. Sorry, my brain was just blank for a second, but it's back now. If these events are independent, using and means multiply, then the probability of never and woman should equal the probability someone says never times the probability they're a woman. So let's check it out. If these are equal, then person's response is never and being a woman are independent. The probability someone said never in this example is 0.12. The probability someone's a woman in this example is 0.53. And so we want to check, is the probability of never times the probability of woman here, does that actually equal 0.0636? I mean, I'm grabbing my calculator. I know that it does equal because, you know, like I did this already, but just in case you don't believe me. So it turns out that this and means multiply rule works. The probability of never and woman, that red number in the table, does actually equal probability of never times probability of woman. So that means these events are independent. Now that's only that's like half the battle. That's maybe the easier part, showing the formula or the math. Then we got to write it up. When you're writing in stats, my advice, we always need context. So my advice is to reword the question. So I would start by writing the events of being a person whose response is never and being a woman blank independent, either are or are not. So all I'm doing right here is I literally am just copying this wording. And that's some of my best advice that I could give you, is to copy the wording out of the question. That way, right, we don't have to like waste our brain power on how to rephrase this. That's a waste of time. Don't be lazy, copy all the wording, because now, right, we have context. There's no way we're going to mess up the context if we pull it right out of the question. The other thing is sometimes students don't directly answer the question. So by pulling out this wording, I'm using good context, but also now I'm directly answering the question, saying these events either are or are not independent. And in this case, these events are independent. And our reason is pretty much what we've shown in math, because the probability of woman and never equals the probability of woman times the probability of never. Now that last sentence, this last piece I wrote here, I could have written that in mathematical notation. I'm typing, so I didn't, right? But this last piece in red, I could have said because, pretty much what I wrote over here. I could say because probability never and woman equals probability of never times probability of woman. Like, let's say I make a mistake and I didn't use the intersection. If I use the union by accident, now my explanation is incorrect because union doesn't mean and. So you could use the notation, but if you have any hesitation about that, just don't use the notation, because if you use the wrong symbol, you're going to mess up your whole justification. So that's one way, and we're using our answer from A1. I could have, no, I couldn't have, because it specifically said woman and never. Just pretend I didn't say anything there. So that's one way. But that's not the only way we might have approached question B. The other option would be to use the independence formula idea. And so similarly, in question, we can use a previous answer. In question A3 in this 2019 example, we found the probability that someone's response was never given they were a woman. And so for that question, probability of never given woman, just a little side note here for conditional, the numerator is always both. So the numerator is never and woman, which is going to be 0.0636. The denominator is the total for like the given thing, even though this isn't really a fraction. If we view this as a denominator, it works. And so the total for women was 0.53. And 0.0636 divided by 0.53 comes out to be, 0.12. So based on the independence formula, if response is never and woman are independent, then like the given a woman shouldn't matter. It shouldn't change the probability someone responded never. Or in other words, probability of never given woman should equal the probability someone says never. And if we pull that from our table up here, right, we see 0.12. So these are equal. As I write this up, I really wish that I copy and pasted the text from before, because I'm going to do the same thing, right? So I'm going to say the events of being a person whose response is never and being a woman are independent. And why is that the case? Now we got to explain our reasoning. There's our mathematical support. I mean, I think if we leave what we have here with the math support, like we have a mediocre answer at least. That's not an I, that's not incorrect. But of course, we're shooting for 4s and 5s in the exam, not 2s and 3s. Because the chance a woman says never, right? The probability someone says never given they're a woman is the same as the chance a random person says never. What we're saying here is if we know you're a woman, you have the same probability of responding never as overall. I could have written that. I could have written if you're a woman, you have the same chance of responding never as overall, or maybe as a random person. Right? That would just be another way to word this. That's it. 2 options. Do it either way. Now, last little side note here is it would be mathematically correct if I wanted to. It would be mathematically correct to look at what's the probability someone's a woman given they said never. I could then compare that to the probability of woman. So this, well, woman given never, that N looked like a W. This would also work. The only reason I didn't take this approach is previously in A3, I had already found this probability of 0.12. So why do extra work and do something different on a timed exam when I can already use an answer that I had found previously? But if you don't trust me, right, try this out. Do woman and woman given never. It should equal the probability of woman, right? Because we've already shown these are independent in 2 different ways. So the third way should show us the same thing. So I like that example with the two-way table from 2019 because we can apply both strategies for determining independence or establishing independence. But it also gets us into some test stuff, right? Using previous answers and getting into some other writing. All right, let's try another one. This one's in, for my students, this one's in that like packet we've been taking notes in with the tree diagrams, Venn diagrams and all that. It's at the end if you want to write it on there. So, I mean, of course you should just pause the video and try this without me, right? Like that's obvious at this point. That's how we engage in these things. We want to know are having a data display and having an equation independent events. So 2 options. We could look at probability of display and equation should equal probability of display times probability of equation. So in previous examples, many of us have been trying to multiply when we shouldn't. We can't really use the animated multiply rule unless we know the events are independent. Here, we'll check. Probability a page has a data display is 0.48 times the probability a page has an equation is 0.27. And so on the right side, 0.48 times 0.27 gives us 0.1296. On the left side, though, the probability that a page has a data display and an equation, right, that intersection means and, is right here. 7% of pages had both a data display and an equation. And in this time, these do not match. And so if I were going to write this up, I would say having an equation and having a data display are not independent. They're not independent. They probably are related because the probability of display and equation does not equal the probability of display times the probability of an equation. Some of us are going to think that's the easiest approach. Some of us are going to like the independence formula. Whatever. Sometimes, some contexts, we have to use one way or the other. the examples we've looked at, we could take either approach. For here, like that's what we did, probably easier, but we could look at what's the probability a page has a display given it has an equation. So that's going to be display and equation, right? The numerator for conditional is always both. So that's going to be 0.07 over the total probability that, right? That's not really for fraction, but it works, of an equation, which was 0.27. And so that gives us, right, something close to 25% because it's almost 7 out of 28. So that gives us 0.259 on the left, but that should equal, if these events are independent, that should equal the probability that a page just has a display, right? The given equation shouldn't affect anything if these are independent. However, the probability that a page has a data display is 0.48. And of course, 0.259 does not equal 0.48. So here we could say having an equation and a data display are not independent because, don't write that sloppy on the AP exam, what this shows us, a page is less likely to have a display if it has an equation, right? That's what this is showing us over here on the left. If we know a page has an equation, there's like a 26% chance that it has a display. But overall, there's a 48% chance some page in this book has a display. So if we know it has an equation, it decreases the chance of having a display. So they must be related because having an equation lowers the likeliness that this page has a data display. And of course, we could also flip it. We could look at the probability a page has an equation given it has a display. That should equal the probability that it has an equation. And I'll leave that one for you to try out for fun because that'll be awesome. All right, one more. Here we have, I Googled AP statistics problems. I was trying to find a nice two-way table, and the website they came up was my own blog. That was kind of cool. No one else cares about that except for me. So here we have a free response from 2017, pretty recent. I will tell you that by the time you take the AP exam, I think most of you are going to address this question. Do the data provide convincing statistical evidence of an association between age group and gender and the diagnosis of schizophrenia? I think most of us are probably using what's called the chi-squared test for independence to do this. That's going to feel pretty easy by the time we master hypothesis testing in the spring, but we don't have to do it that way. A chi-squared test for independence is a little better because it's not going to focus on just one specific kind of cell, as you'll see in a second. So here it's a little more open, right? We got to narrow down like what we should use, like in 2019 Part B. So we've got some data here looking at a random sample of 207 men being treated for schizophrenia. We have the age and gender when they were diagnosed with schizophrenia. A lot of options here. Chi-square test for independence, best option. But I could say, look at what's the probability, so I could use and means multiply. And I'm just like picking random stuff. Like, I don't know, which number do you want to use? This one? Sure. So that would be the probability that someone is a woman and is 40 to 49. Probability someone's a woman and is 40 to 49 would be 21 out of 207. That should equal, if these events are independent, right? That should equal the probability. I mean, like if you were in the room right now, I'd be asking you, right? And hopefully you're thinking about it, pausing the video on your own, trying this. That should equal probability of woman times probability someone's 40 to 49. Probability someone's a woman is, right, 119 total women out of 207 people times probability someone's 40 to 49 is 30 out of 207. So we want to figure out, are these equal? On the left side, 21 out of 207 is 0.101. Oh my God, I'm sitting in room 101 right now. On the right side, 119 out of 207 times 30 out of 207. Make sure you use parentheses around your fractions if that's how you're rolling. Gives me 0.083. Now this one's a little bit tricky because these two numbers don't have to be exactly equal. They got to be roughly equal. And so now the question becomes, are these far enough apart for us to say that they're different? Like some people might look at this and be like, 10%, 8%, those are pretty much the same thing. And in some situations, 10% and 8%, whatever. In other situations, 10% to 8% is a big difference. Like if I'm going to give you a raise, 8% and 10%, you might care a lot about that extra 2%. So what do we think here? I mean, if you write up, and again, reword the question, that's like really important. Reword the question, do it, or I'm going to just do it. So we might say, now, is there an association? So this doesn't use the word independent, right? We're trying to think, are these related? So if there's an association, that means related, that means not independent. So the vocab can be tricky. So if we wrote, there is an association between age group and gender in the diagnosis of schizophrenia. There is an association. These are not independent because probability of woman and 40 to 49 does not equal probability of woman times probability of 40 to 49. Like that's a correct justification. That's what I'm looking at. Whereas honestly, if I were grading these, and this is, again, this in the AP exam, this ambiguity wouldn't be an issue because you're going to use something called a p-value and a chi-square test of independence. If one of my other students wrote, there is not evidence of an association, or in other words, said age and gender are independent because the probability of woman in age 40 to 49 is about the same as woman times 40 to 49, right? If someone interpreted this as saying these are about the same, roughly the same, I'm not going to stress too much about that. I don't know that I agree, but they understand the concept, and that's what's most important. So a couple takeaways from this, right? Like I just picked the 2021. Like you could have used any blank and blank, right? You could have done man and 30 to 39 or women and 50 to 59, right? You could have picked any one of those categories. But again, that's why the chi-square test is ultimately going to be better because we're not just isolating one specific number out. Whereas in this example, we didn't have to worry about that in the 2019 example because they already isolated that specific spot for us, right? They isolated never and woman. So they kind of narrowed it down for us. Whereas if we're just given the 2A table, it's much more wide open. Lastly, gonna do this question with the independence formula, right? I could have looked at, and again, I'm just kind of picking random, not random stuff, but like I could do man given 50 to 59. I could do man given 30 to 39. I could do women given any of the age groups. I could do the age group first, right? But this should equal the probability someone's a male. Probability someone's a male is 88 out of 207. We don't need a conditional formula for this. If we know the person given 50 to 59, we're only looking in this category. And if you're 50 to 59, out of those 15 people, 3 were male. So this is 0.2. 1/5 of 200 would be 40, right? And that's way more than 40. So this is probably going to be bigger than 0.2, right? Like this is almost twice as big as 0.2, but who cares about all that mental math I'm saying anyways? Just do 88 divided by 207 in your calculator and you get 0.43. So here, I'm going to say, let's write it up this time. So this time I might say, there is evidence of an association, not independent. You don't have to use the word independent. I'm just doing that because, you know, tying in the independence vocab. But there is an evidence of an association between age group and gender in the diagnosis of schizophrenia. Copy the wording from the question because if someone is 50 to 59, they are less likely to be male than overall. I remember it's not just about age. I don't love this wording because it kind of leaves like if someone is age 50 to 59 at diagnosis of schizophrenia. Right, that's what this is, right? This is the age at diagnosis. says it right here, right? Age at diagnosis, that's where I'm getting that from. But if we know someone's 50 to 59, there's a 20% chance they're male. Overall, there was a 43% chance these people who were diagnosed were male. So if we know someone's 50 to 59, it appears, point two, they're less likely to be male than overall. That's it. And I'll say one more time, on the AP exam, you wouldn't even really be doing what I'm doing on the screen here. I'm just using this example to show us these probability formulas. This 2017 free response, probably chi-squared test for independence. Something like this, pretty easy to apply these probability formulas, or this 2019 question, you could, for 2019 part B, probably do a chi-squared test, but that's going to be really time consuming and waste your time. For part B, because they really isolated the never and the woman, that's why it lent itself to this kind of probabilistic approach using and means multiply or the independence formula. That's it. That's all I got for you today. I'll leave you with this quote that I love from Macklemore. I hear so often that students are like, oh, I'm just not good at math. Like, yo, that's not how it works. People aren't just born great at piano. I mean, maybe they have some natural talent, of course, but how do you become great, right? You practice, man, you practice. So maybe you're not great at probability yet. You're not going to just wake up one day and be great at it. Practice. Macklemore. Soak it in. Keep soaking while I stop sharing before I click end. Have a great